Enjoy.
Subhashish.
Yep.
Julie told me that the mass of a carbon atom is 12. How many like 12?
12.000.
Zero.
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 Lots of zeros.
That seems like a big coincidence.
Right.
Was that a coincidence?
Is it a coincidence? Or
why is carbon so good at that?
Yeah, let's talk about it. So one of the things that we'll start with today in beginning to talk about nuclear chemistry is how carbon is basically how the mass of carbon is the definition of the atomic mass unit.
Whoa.
So last time we briefly introduced this when we talked about the mole. The definition of atomic mass units, which is our scale for the mole. Remember, the mass of a carbon-12 atom, we said last time, is equal to exactly, and this is what Miriam and Subhashish were just so surprised about, exactly 12.000 grams. So it's equal to 12 exactly. And it turns out that carbon is actually the definition of the atomic mass unit scale. This carbon-12, so this means it's the isotope of carbon that has 6 protons and 6 neutrons in the nucleus. Of course, if we're talking about an atom, it also has 6 electrons. And so the mass of the particles, so the sum of the mass of the particles, if we add these all together, the mass of these individual subatomic particles, it equals 12.09900 AMU. So did we all just lie to you? So what's the difference here? So we said that the mass of a carbon-12 atom is exactly 12. That's the definition of the AMU scale. But when we sum up the individual subatomic particles, it's a slightly different number. And we call that the mass defect. So the carbon nucleus has what's called a mass defect of this difference. So the mass defect is this 0.09900 atomic mass units. And just to remind you, AMU, so this is equivalent to grams per mole, which is the more common way that we talk about that. So an AMU is a gram per mole. So that mass defect, what this means, this missing mass is the energy that it took. This missing mass is the energy that binds the nucleus together. So the reason it's not exactly 12, the reason the mass of the carbon, the reason the sum of the subatomic particles is not exactly equal to 12 is that the difference is the energy binding those nucleons together. And so what this means is we can look at these mass defects. So the utility of this is we can look at the mass defects of nuclei, and that tells us what the binding energy is of the nucleus. So to extend this notation a little bit, so if we take a C12 nucleus, another way to write this is with the subscript 6, which shows us the number of protons directly. So that's the atomic number, or the charge. So this is the number of protons. And this is the total number of nucleons. So this is the so-called mass number, which equals the number of protons plus the number of neutrons. And so we break that up. So we imagine the hypothetical. So this is a hypothetical reaction. Breaking up into 6 protons and 6 neutrons. And so I'm using the same notation here to say I've got the number of protons in the subscript, so there's 1 in a proton and 0 in a neutron, and the mass number as the superscript. And so these are just to remind you of the terminology that we've been using, these are the nucleons. And so this is a hypothetical reaction, and so this would correspond to, this is the reaction you're doing when you blast apart a nucleus. So if we are overcoming the strong force that holds the nucleus together and breaking it up into these constituent pieces, that's this hypothetical chemical reaction. So think for yourself, what would you expect the sign of the delta E for this reaction to be? Would you expect it to be a positive number or a negative number? So remember that a positive delta E is we're putting energy in to go from reactants to products. A negative delta E would be a reaction that gives off energy. So do you think you need to put energy into this process, or does this process release energy? So analogous to overcoming electrostatic attraction to ionize and remove something from a nucleus, here we have to add energy. So this is a positive delta E. And in fact, it's a very large and positive delta E because we have to put energy in to break apart the nucleus. And specifically, this delta E for this reaction, last time we introduced Einstein's most famous equation, E equals mc squared. And so this delta E of this reaction, which is related to this mass defect, so it's related to the change in mass that accompanies this reaction. When I take apart these nucleons, they have a different total mass than when they were together as the nucleus, as the carbon atom together. And that's because I have to put in a huge amount of energy to move them apart, and that energy is equivalent to a mass change. So this is the nuclear binding energy. Of carbon-12. Okay, I'm going to erase now.
Go for it.
All right. So because, as we said, that this the delta E for these nuclear reactions is enormous, we can use this actually. So because it's large, we can use the corresponding, well, basically because delta E is so large, that means delta M is large enough to be measurable. And so because delta E is large, we can use the corresponding delta M to calculate nuclear binding energy. I'm going to create an abbreviation here that we can use. So nuclear so the way we do this is for the reaction that we're considering, the nuclear reaction that we're analyzing, we calculate delta M, which just like our sort of naming convention for delta E is the mass of products minus the mass of reactants. So analogous to when we were looking at the Bohr model of the hydrogen atom, we said the energy is the energy of the final state minus the energy of the initial state. So we can look at these nuclear chemical reactions and determine the final mass and the initial mass. So let's look again at our carbon-12 example. And we're going to make a small change to the total reaction. So because this symbol here, and let me also introduce a little bit of terminology. So this is a specific carbon nuclide. So a nuclide, the nuclides are all the isotopes. So we're introducing two new terms here. All the isotopes of an element. And so this is a nuclide symbol. So what I've put a square around here is the symbol for one of the carbon nuclides. So that's nuclide, and isotopes in turn are atoms with a different number of neutrons. So atoms of some specific element with a different number of neutrons. And so what that means is this carbon-12 nuclide is also the 12 isotope of carbon. So we can also have a 13 isotope of carbon, which would have one more neutron in the nucleus. Okay. To see an example of this, see page 2 of the lecture PowerPoint, which shows the belt of stability, the so-called belt of nuclide stability. And what this shows, if you look at the, the belt or isthmus of stability, I will briefly show this to you, and you've got it in your handout, that at certain proton numbers, so that would be the 6 here. So for example, for 6, we can see that there are a series of different spots. So carbon has multiple isotopes, so multiple different neutron numbers for that proton number of 6. And so this shows that there are a lot of different isotopes at many masses. So these are all of the radionuclides. And the other thing that's shown here are the darker colors in the middle are the relatively stable nuclei, and the orange colored ones, so the outer band of this isthmus of stability or belt of stability, are the radioactive nuclides, and so those are less stable ones. And so what we see along the middle of this belt is the region of most stable nuclei. And so this is plotted as number of protons and number of neutrons on the y-axis, and so we see that some have multiple stable nuclei, and that they sort of trace this line that is actually not along the 1-to-1 line of neutrons to protons. So this is one of the interesting things here, that nuclei actually turn out to be more stable with a slight excess of neutrons relative to protons. And we can think about this a little bit in terms of electrostatics. The protons are repelling one another electrostatically, while the neutrons and protons are all equally glued together by the nuclear strong force. Okay, so brief segue on the belt of stability and what we can learn there. And now let's return to our nuclear reaction. We're going to take apart a carbon atom. And so this is now going to be a carbon atom. So it'll be the mass of the nucleus plus 6 electrons. So if we have a neutral carbon atom, because there's 6 protons in the nucleus, there also have to be 6 electrons. So when we take that apart, now instead of splitting it up into protons and neutrons, I'm going to split it up into a hydrogen atom and then 6 neutrons. So you'll see my nuclide count balances in exactly the same way. The only thing that's different here is that this is the mass of 6 protons now plus 6 electrons. So what I've done here is I've made it so that I have electrons on both sides of this equation. That's useful because the electrons cancel. So I still have a balanced chemical reaction. The electrons cancel out on both sides. But what I've done now is made it so that I can measure the mass of a carbon nucleus and use that as the mass here, and the mass of a hydrogen atom, rather than the mass of a bare, so that for my reactant here, I can use the mass of a carbon atom, including its electrons, rather than having to somehow ionize all those electrons off, which, as you know, requires a lot of energy, and then measure the mass simply of the nucleus. And so this gets me the advantage that I can use mass of the carbon atom instead of needing to somehow get carbon 6+ ion, take all those electrons off. Okay, so now what I can do is look up, so the mass of a hydrogen atom is equal to 1.00783 AMU. So this is using my atomic mass unit scale. Again, this is equivalent to grams per mole. And so now if I want to figure out delta M for this reaction, it's mass of the products minus mass of the reactant. So delta M will just be the mass, will be 6 times the mass of a hydrogen atom plus 6 times the mass of a neutron. So because I've got a hydrogen atom here, I've got my electrons accounted for. So those are all of my products, and then minus the reactants will just be the mass of a 12 carbon nuclide. I can look these values up. I've got my mass of a hydrogen atom here. So this will be 6 times the mass of a hydrogen atom, 1.00783 AMU. We had the mass of a neutron a few weeks ago in class. So I'll just remind you, in AMU that is 1.00867 AMU. And then minus 12.00000, etc. AMU for my carbon atom. So here's where I get that mass defect that we talked about. So the delta M is plus 0.09900 AMU. So that's the mass defect. That is the change in mass that is observed when you blast a carbon atom apart into its constituent nucleons. So now I want to calculate delta E from this. So delta M I've just calculated. So C, remember we had 2.998, that's the speed of light. So the relativistic relationship that Einstein posited for this famous equation is that mass is related to energy, and the proportionality constant is the speed of light squared. But these are not very useful units here if I'm talking about AMU, atomic mass units, and I want to convert somehow to an energy unit. So we need new units. New units for the speed of light. And so I'm going to ask you to, on your own, go through the calculation of converting the speed of light from this unit. So I will give you the conversion, I will remind you the conversion factor that 1 joule equals a kilogram meter squared per second squared. So that's one useful conversion factor. And then the AMU, so the atomic mass unit, we can convert that into kilograms, the macroscopic scale. So 1 AMU is equal to 1.661 times 10 to the minus 27 kilograms. So using those two conversion factors, see if you can calculate C, see if you can verify the new value of C that I'm going to tell you here, which is that C is equal to 931.5 mega electron volts per AMU. So use those conversion factors and our known value for speed of light and see if you can confirm that that agrees while I erase this board. Okay, were you able to verify the new speed of light units? Great, let's use it. So now we can calculate that the binding energy, so the nuclear binding energy for this C12 isotope is now the energy. The delta E for that, which is the nuclear binding energy, is the change in mass times C squared in our new units. So if we put back our mass in AMU, use our new conversion factor, so C squared in these weird units, but you've convinced yourself that they work out, and now you see that these are units that are custom made to go from atomic mass units to mega electron volts. Mega is the 10 to the 6th exponent, as you discovered when you did that unit conversion, that units conversion for speed of light. And so mega electron volts, so these are huge amounts of energy. And so the fact that our preferred new units for C squared involve mega electron volts tells us the kinds of energies we're talking about here. And when I work this out, we get an energy for this, nuclear binding energy for this nuclide of 92.2 mega electron volts, because my AMUs cancels out. Importantly, remember that this change in mass was positive. So when I blast apart a carbon nucleus, there's actually more mass in the products than there was in the reactants, which seems a little weird. You've probably heard the idea that mass is conserved. So mass is conserved, but in this case, there's such a huge amount of energy that we put into that reaction that it manifests as a small change in mass that corresponds to that difference in energy. Okay. So the real, where the buck stops is really that energy is always conserved. And so when you have such enormous, in normal chemical benchtop reactions, we would observe that mass is conserved because we would never see these huge energy exchanges that would correspond to a measurable mass. So energy conservation is really the bottom line. Okay, so this is large and positive. So the fact that this is a positive energy means energy is required to blast the nucleus apart. So I have to put energy in to do that. The nucleus is very strongly bound together. So this is analogous to energy required to overcome the electrostatic attraction of an electron to the nucleus. And that was the subject. In our last week. The electrostatic attraction of the electron to the nucleus is the ionization energy. And so remember, ionization energies were always positive. You always have to put energy in to pull an electron away from the electrostatic attraction of the nucleus. Similarly, we have to put energy in to pull those nucleons out of their strong nuclear force that is holding them together. So analogous to this electrostatic attraction, so just to remind ourselves, ionization energies, do you remember approximately what order of magnitude those ionization energies were? So for hydrogen, for example, the ionization energy from the lowest n=1 state was about 13.6 electron volts. So ionization energies are of order 10 to 100 electron volts. And here we've got mega electron volts. So we're a million-fold higher energy. Larger energies than these ionization energies. So lots more energy required to blast the nucleus apart. To compare the stability of nuclides. So let's go back to this, this idea on the belt, the isthmus of stability, the belt of stability. To compare stability of nuclides, we want to look, instead of looking just at this pure total amount of energy to blast apart carbon, we want to look at nuclear binding energy per nucleon. And so what this does is effectively normalize out the number of nucleons. And so for example, if we have a much heavier, more massive nucleus, it will be much harder to blast apart because you're overcoming many more nuclear strong force interactions. But we want to know what's gluing it together per nucleon. So we want to normalize that out and be able to compare, say, carbon to iron, which has many more nucleons in the nucleus. We want to say which one is relatively more stable to the number of nucleons. And so for carbon-12, for our carbon-12 example, this would be plus 92.22 mega electron volts. And how many nucleons are in the carbon-12 nucleus? That's easy. That's always going to be the superscript. So there are 12 nucleons. Remember, that's just protons plus neutrons. And so this is 7.685 mega electron volts per AMU. And so because each nucleon, or per, we can just say per nucleon. We don't have to say per AMU. It also is effectively per AMU, but that's how many mega electron volts per nucleon. And so what you'll see on slide, on page 3 of your PowerPoint, of the PowerPoint that I distributed with this, you'll see another plot which shows the thermodynamic stability in terms of this value that we've just calculated, the binding energy per nucleon, which gives us that kind of normalized quantity per how many nuclei in the in the nucleus of the atom, how stable is it? So let me ask you, what would be the nuclear binding energy per nucleon of a proton? So we had the mass of the hydrogen atom, a proton, that we looked at before. So what would be the nuclear binding energy of this? Give that some thought. Aha, it's a trick question. What would you be bound to? If there's only one proton in the nucleus, there's nothing to bind it to. So the nuclear binding energy here, 0 nuclear binding energy, because only one nucleon. Okay, so that was a trick question. Instead, so if we look at this PowerPoint, what is the most stable? The most stable nuclide of all. So we could say, what is the most stable nuclide of all? We could say 0 nuclear binding energy. This would be the least stable. You don't get much less stable than 0. And so you can imagine that proton would be at the left-hand axis of this graph on page 3 of your PowerPoint. So what is the most stable nuclide of all, looking at this PowerPoint? Take a look at it. Give that some thought. So the most stable nuclide of all is the one that occupies the highest position on that y-axis, which is iron 56. So the 56 isotope of iron is the most stable nucleus of all. And this just has to do with that nuclear binding energy being optimum, optimizing the trade-off between the nuclear binding energy, holding all these nucleons together, and the electrostatic repulsion that's pushing the protons apart. So you can see that past iron, things turn over a little bit and nuclei start to become less and less stable. And so those are nuclei where the electrostatic repulsion of the protons is winning out. And so the most stable nucleus of all is this iron 56, which means, so let's see, most stable nucleus of all, which is equivalent to saying it has the largest nuclear binding energy per nucleon. So those are equivalent statements. So when I say it is the most stable nucleus, what I'm saying is it has the largest binding energy holding that nucleus together on a per nucleon basis. So a consequence of this would be, if this is the thermodynamically most stable way for all the protons and neutrons in the universe to organize themselves, and electrons in the universe to organize themselves, that means we are all becoming iron. So iron is the most stable configuration of all the subatomic particles. And so thankfully, very slowly, the whole universe will tend towards this most stable nuclei of all. But it'll be a while before we all become iron, because there's some kinetics to overcome. Okay, so if we return to that belt of stability and look again now at what we've got here, so we can see our iron nuclide. So 56 number, well, we'd have to figure out what the number of protons is for iron and look it up on here. So that's the most stable. And then we can see that as we go to higher and higher masses, we're diverging in the direction of more neutrons relative to protons. So especially above iron, but even below iron, there are unstable nuclides at each proton number. So remember that the proton number is what defines an element. So each column here would be a different element. And so at, for example, 10, there would be stable nuclides, but then many unstable nuclides. And so those nuclei that are inherently unstable so those nuclides undergo the way that they become more stable. So we can think of, so with higher excited states of atoms with electrons in a higher energy level, we said that they'll drop down to a more stable energy state. So for an inherently unstable nucleus, the way to become more stable, the way to overcome that inherent instability and fall down to a more stable state is to undergo radioactive decay. So you can undergo radioactive decay to transform from a less stable nuclide into a more stable nuclide. And the time scale of this process is specific to the nuclide. And so this is really what we mean by radioactivity and unstable nuclei. It's basically just a matter of time scale. It's how rapidly is that nuclide transforming into, how rapidly is it transforming into another nucleus. So we said iron is the most stable of all. So everything could sort of gradually tend towards iron, but at different rates. And so the time scale of radioactive decay we can summarize as, I'm going to do one more erase and then we'll finish this. So the time scale is specific to the nuclide, and that is the half-life of decay. Okay, so T subscript 1/2 is how we designate the half-life of a nucleus. And so we can also say that that is the time. So why half? What that means is the time required for half of the sample. So, of course, typically we would have an aggregate of several of some nucleus, and so so T half is the time scale for half of the nuclei in a sample to undergo decay. Another way to look at it is this means that the activity in terms of decays per second as a function of time will have this characteristic behavior. Will tail off because after any given time, because there's a certain characteristic time in which we go down to half of the activity rate. And so this would be, if this is 1, if we start off at some arbitrary unit of 1, and then the time it takes to go down to 1/2, or 0.5, is the half-life. So it's that characteristic decay time. What you should notice is the time it takes to go down to, if I've drawn this well, the time it takes to half again is now, so this was the half-life once. Here's another half-life. It's the same time difference. Okay, so we can read the half-life off of the plot, but then we can see it constantly keeps halving. And so this is an exponential, this is an example of an exponential decay function. And next semester in Chem 102, you'll spend a lot of time thinking about these different characteristic reaction rates. So this is an exponential decay. So the activity, so this is sort of a mysterious quantity that I've introduced here. So what do we mean by the activity? We said it's the characteristic time of undergoing decay. What is exactly this decay? So radioactive decay, we will talk a lot more about next time, the different types of radioactive decay. But basically it is that this nucleus spontaneously spews out particles. So we'll talk about what those particles are next time, that it can spew out. But it can spew out particles, and it can also spew out gamma rays, which, remember from your study of the electromagnetic spectrum, that's very high energy light. So it spontaneously spews out particles and gamma rays, and in the process of that, it transforms to a more stable nucleus. So these are processes that actually change the subatomic particles that are in the nucleus. So we're actually spewing out particles and gamma rays in a way that transforms the nucleus into a different element, right? And what determines which part of the nucleus is it that determines the identity as an element? It's how many protons it has in it. And so these radioactive decay processes actually involve converting between protons and neutrons. So this makes a little bit more sense in the idea that these nucleons somehow, remember we saw that they had about the same mass and they're sort of equally likely to be attracted to one another with the nuclear strong force. So there is some similarity between them, and now it turns out in these very high energy nuclear reactions we can actually interconvert neutrons and protons. So we'll talk more about that, the details of radioactive decay next time, but just to give you some typical half-lives, just to know what's out there, what kinds of half-lives do elements have. So iodide 131, which is a commonly used medical isotope, has a half-life of 8.02 days. And so this is used for thyroid treatment. And in fact, I think the Reed chemical reactor makes some of this particular nuclide. It's used for thyroid treatment, and that half-life is very helpful because it gives a time scale that's relevant to the treatment schedule. Strontium 90 is another very valuable radioactive nuclide. Its half-life is 28.8 years. So just to see, first of all, that these half-lives vary over orders of magnitude, so 8 days versus 30 years, basically. Strontium is a very valuable radionuclide for atmospheric chemistry. It was produced in the stratosphere when nuclear testing was happening. Nuclear bombs were tested in the stratosphere. That created a spike of this strontium-90, which is not a naturally occurring isotope, but it created it specifically up in the stratosphere. And so it's very valuable now to atmospheric scientists as a tracer of exchange of air between the stratosphere, which is the upper atmosphere, and the lower atmosphere, troposphere. So we injected a whole bunch in 1960, and now we can sort of watch as it spreads around the globe, and that gives us some information about atmospheric circulation. Uranium-235, perhaps a rather famous isotope. So this is a stable, relatively stable isotope of uranium. The half-life of this is 704 million years. So that's sticking around for a while. So this is among the longer half-lives. The shortest half-life, shortest known, and you've got to somehow be able to make this in order to measure its half-life, is the 4 isotope of hydrogen, which has a half-life of 100 yoctoseconds, an obscure unit prefix. So that's 100, and yocto is 10 to the minus 24. So that is not a lot of time. That guy does not stick around long at all. Okay. And just to remind our nuclide designation. So the symbol 4H, that should be a superscript. So this means that the mass number for total of neutron plus proton, because it's hydrogen, I don't need to write the subscript because hydrogen tells me, the atomic symbol tells me that there's 1 proton. And so that means this must be, so this is the isotope of hydrogen with 1 proton and 3 neutrons. That's what that tells me. And so I could figure out the nuclear binding energy for that by splitting it up into 1 proton and 3 neutrons. That would give me a binding energy for this guy. Just pulling all those subatomic particles apart. Okay, so radioactivity ranges, timescales of radioactivity range over multiple orders of magnitude. This is just a way of telling us that one way we can think of it is everything is radioactive. It's just a matter of time scale. And so some things last a lot longer than others. But someday we will all be iron. And with that, we'll close for today.